Welcome everyone, and I'm especially thankful that you guys are here, despite all the cool stuff happening outside, free beer, lockpicking, everything. A little bit about myself. I'm Arpita Biswas. I work as a security researcher at Palo Alto Networks. I deal in system security, firmware security, looking at packets, network security, the whole range of it. And today we are going to talk about firmware security, right? This is a very weird area. It's not hardware, it's not software, it's somewhere in between. And for many of us, including me, it was a steep learning curve. So if not anything else, I hope today that as you walk out, you know that yes, the learning curve is steep, but at the same time, here are some ways to get started with it, right? Cool, so let's get started. First, I'll walk you through the outline. The system architecture. Where does firmware fit into this whole hardware-software land? Then we'll look at two common flavors of firmware. One is BIOS, and then the newer version that's UEFI. We'll look at a few attack vectors, how they attack. Having seen those, we'll look at the defense vectors. Then we'll go through a few open source tools that I found very handy. And finally, if you guys want to tinker with the SPI chip and try to read and write your own firmware, how would you do it? And then we'll open it up for discussions. OK, so system architecture. As you can see, there's this layer of hardware that you can touch. You have your laptop, your desktops, your PCs. You open it up. You can see the fan, you can see the network cards, you can see the VGA and all that stuff on it. On the other hand, when you interact with you have the user experience, right? You have the screen, you click on buttons, and you interact and make it do things or watch YouTube videos. But between these two ends, there are a lot of things that happen. So every time, for example, you open a dock, it goes to the system call, which is kind of an API exposed for the user applications. It then goes and gets all the components work together to create a file, goes to the hardware abstraction layer, which then talks to the firmware of your hard drive and says, hey, listen, I need to open a file, so give me XYZ MB of memory space in it. And this dance happens back and forth every time we interact with computers. But the most crucial part that we're going to look at today is the firmware. And it sits closer to the hardware, but it still interacts with the software. So it bridges both these worlds. The first flavor, BIOS. BIOS is basic input-output system. And I'm pretty sure a lot of us have seen this screen. A lot of blue text haunting our childhood. But, but behind this, there's a series of complex dance that happens. So when you power on, it goes and fires up the circuitry for your SPI chip, which is Serial Peripheral Interface. This chip holds your first instructions that is executed after the power switch is on. So this SPI chip loads all the instructions it has on it into the CPU registers at a particular preset address, and that's called as the CPU reset vector. That's a huge hexadecimal number out here. Once that happens, then there's kind of an inventory check that's done on the chipset, right? So it's called post-operating self-test, power on self-test. And at this point, all the guy is trying to do is that, OK, I have 10 things on my chipset. Which of them work, which of them don't, and what's the error? And set it up for the rest of the code to take over. Then we have the CMOS. This is the second piece of non-volatile memory that's in your chipset. It holds information about your BIOS, as in, for example, 3 operating systems to boot. Which of those needs to be booted right away is what the BIOS, CMOS holds about the BIOS. Then, having known which operating system to load, it goes ahead, puts all those instructions at 7C00, boots up, gets everything ready for the operating system, and you can log in. So roughly, these are the 4 or 5 steps that happen on a BIOS. Moving on, by the way, we are looking at the SPI. One of the attacks is on the SPI chip. The second attack will be on the CMOS chip. So keep in mind. Moving on, we have then coming up was the newer generation of firmware, which is Unified Extensible Firmware Interface. Here, things have been tried. So BIOS is a very monolithic piece of code, right, which has preset address and everything. Slowly, it started getting bloated up with all the legacy code. Then UEFI happened, and we had a snazzier screen. But behind this, we also had a couple of newer options. It was faster than BIOS. It's more secure. You have an option to pre-verify what firmware images you load before you execute them, kind of making it a bit more secure. So similarly, when we power on, the SPI chip loads on, boots up, sets up the code at the secure stage. Then it goes and does the inventory check, which is the pre-EFI stage. Then we have the driver execution engine. This is another crucial part. Here, the driver execution engine doesn't care how you initialize it. It says, OK, I see a VGA, I see a network card. You guys go ahead, initialize, and come back to me with the error code, if any, or let me know if it's working. So it's completely agnostic of what's happening inside the initialization code, and hence it decouples the firmware initializations. Then we have the boot device being selected from the CMOS, like in BIOS. Then the instructions are now executed in a secure shell called as the UEFI shell, which has limited memory protections. Then the OS bootloader comes in, pages up, sets up the paging, the protection and everything, and finally we log in. So roughly between BIOS and UEFI are similar, except that it's more modular, and you have an option to do pre-checks before running those firmware images. Having seen these two, let's look at a few attack vectors. The first, these are commonly known as evil-made attacks, and it requires you to reflash the BIOS on your SPI chip. How do you do that? Sometimes in some chipsets, the write protection bit is off, or it's partially write protected, not the entire region is write protected. And then you also have physical access to the chipset, and you use something like a bus pirate or a DediProg or a Minoboard Max, which is something like this. This is a DediProg, by the way. DediProg with a flash clip, bus pirate with a flash clip. I actually have my own setup here too. You guys can take a look at it later on. But this can read and write your firmware on the chipset, provided your SPI chip is not write protected. Now, since this comes in at such a low, at such a starting point, any changes to the firmware and henceforth makes everything very persistent, stealth, very difficult to remove, and hence making it very difficult to detect as well. The next vector. Now, access to the chipset. So you can still do a remote BIOS update. There's a mechanism for it. You just hack it. So you have a laptop. You download your the firmware update onto your laptop, but then that's a malicious piece of update. Well, nobody cares, and then the BIOS goes ahead and marks the CMOS bit as the update bit as on and says, hey, listen, the next time you reboot, the firmware sees the CMOS has the BIOS update bit set. So it says, okay, I have an update pending, goes ahead, triggers an SMI. So what's an SMI? SMI is System Management Interrupt, and it's a mode where you even bypass the operating system and has higher privileges than operating systems. And that mode is called as the System Management Mode. So once your processor enters the System Management Mode, there are absolutely almost zero checks. So you can then go ahead and recompile your BIOS, that BIOS update, in the SMRAM, which also, SMM also has an area pre-allocated for the BIOS updates to happen, and that's known as SMRAM. And finally, you boot, and nobody is any wiser because it was a regular BIOS update. So this attack can happen remotely. Now coming to the third attack. This particular attack is only for UEFI systems, because this hooks on to the driver execution engine. How? So okay, by the way, this was seen in the wild, as in we have seen a few malwares which are the arcade loader types. Like the previous attack, we download the infected payload on the disk. Then we modify the UEFI's CMOS bit and also the DXE bit. So remember in UEFI, the DXE says, OK, here are the 10 cards I need to initialize. I don't care how you do it. Similarly, the malware goes ahead and attaches itself to as the 11th initialization module. And it says that, OK, so when you boot up the next time, instead of booting up the regular NTFS hard drive, which has your the good operating system, boot up mine, and that has the bad operating system. And now that you have booted up, you have no way to know whether you're in the good operating system or in the bad operating system. So this was another another attack, so pretty interesting in my opinion. But having seen these attack vectors, there's still some ways to make sure that, or at least to know how bad the security is in your chipset. So let's look at a few defensive approaches. First, please make sure that you have your BIOS and system passwords on, so that anytime anybody tries to update your box, you have to manually go in, put in the BIOS BIOS password, and only then update your machine. Sometimes some motherboards also come with chassis intrusion detection. That is, if someone has opened your box in the production rack and put it back again, the next time there's an alert saying that there was someone opened the chassis, and then you know that something's wrong and I better check. Also ensure that your SPI, your alternate BIOS boot blocks, your SMRAM, all these non-regular memory locations are write protected. There is absolutely no reason for them to be not write protected. Then you can also use chipcheck that I'll talk about in a minute to figure out how good or how bad your platform's security is. If you're using UEFI, please ensure that secure boot is on and boot guard is on. So secure boot and boot guard are nothing but a check. So every time you load the next set of firmware instructions, it goes ahead and checks whether the SHA matches the one that's supposed to be. And if it is if the right one, only then it goes ahead and boots it. So if you want to look at chipsec, the tool that I just mentioned, super useful series of Python scripts. You can also check whether your platform is, or your motherboard is. Look at chipset.py. By the way, it's an open source tool that is available. I'll share the links later on. It also has chipsecutil.py, which triggers a few exploits and a few other tools to do memory analysis and analysis of the firmwares that's dumped out. To check whether your BIOS is write protected or not, this is one of the commands. It checks whether the SMRAM, the SPI and the alternate boot block is or not. Then you can also use SMRAM checks. So whether the SMRAM is write protected with the entire region or not. So it's something that looks like this. So the BIOS write enable should be off, and BIOS lock enable should be on. And this is a bad situation. If your BIOS is not write protected, it will show you this huge remarks at the bottom. If you want to check SMM, there are similar checks. I would strongly recommend playing with it. It's a very nifty and very cool set of tools that I found. So overarching all of these, there are a few guidelines that probably everyone should follow if your desktop or your system is one of those crucial ones. Always remember security. So what you need to do is, first thing, ensure that the BIOS has only local updates mechanism possible. There's no way to remotely update it. Once you've ensured that, make sure that the firmware update itself is tamper-proof, as in there's only one way to update the BIOS, and that should be it. There should not be any other bypasses. Third thing, once you know that you want to update, make sure the firmware update that you're giving is a pre-verified, authenticated, digitally certified, however, is a verified piece of software. Then ensure that there is only one SPI and the whole region is kind of write protected so that there's no passing around to write to it. Finally, anti-rollback protection. So once you have your firmware update in, there shouldn't be a need for you to roll back or use the backup, because there has been attacks which use the as malicious with malicious code and then later reboot using the backup boot up. So that's there's no need for that, right? So yeah. And finally, if you want to still play with firmware, having known all these attacks and defense vectors, I use FlashROM. That's an open source that comes with Linux. You can see that it uses bus pirate. It can also sync up with your proc. Hello? One? No? Okay. This is how you can write to the firmware on your spy chip. So as you can see, these are the connections to it. This clip sits chipset. Then this is the bus pirate that actually programs it, and this USB-N sticks to your dev machine, which is where you have your recompiled BIOS on it. So now some open source tools. Google has this huge branch. Their Chromebooks use Coreboot, which is an open firmware. They have a payload called cBIOS, which is specifically for BIOS flavors. Then we have TianoCore, which is for UEFI flavors. We also have chipsec, like we saw a few examples before. Then we have FlashROM. It comes as a default in most of the Linux distributions nowadays. We also have UEFI parser that does a good job of, if you give it an unknown UEFI image, it'll parse out all the ROM and the EFI header and the MCH and all those bins in it. We also have MinoBoard Max. That's another tool that's used, and Bus Pirate, like we just saw. Okay. So now, let's open up for any questions and answers if you still have any gray cells left.
All right. Anyone have questions? Raise your hand.
Oh, I think I need to wait for the mic. If you still want to read up apart from the open source links here, slide, be helpful.
There's one time when I tried to use a SPF like flasher, I had to desolder the chip before it would actually write to it. A lot of times when you just try to clip the chip directly, it will power on other components that would try to tamper with the chip because you are essentially powering on the other components that is reading and writing to the chip at the same time. Have you had that problem at all? I'm just kind of curious.
Lots and lots of times. So what happens? Hello, yeah. So many a times chipsets have their own write protections or their own circuitry, and it's not completely secluded. So you remove the SPI chip from. But that said, there are also a few jumper cables on the chipset. So if you look at yeah, so you have a few write protect jumper cables around if you take them apart. Or use easier to hack chipsets like Google Chromebook. So they do a good job of keeping their core boot code updated with their chipsets that they use.
Do you recommend trying to verify the existing firmware that's on a device to see if it's already been compromised? And if so, how would you go about doing that?
Sure. You should do that in both cases when you want to just verify if everything is all right, and also have a backup of your firmware before you try to write to it so that you can restore. And so what you do is you read out the foobar.rom, put it into FlashROM, and then you can extract out the mrc.bin, the rom.bin, and all those sites, and give it to chipsec. So chipsec does a good job of parsing through the binaries and checking whether the the write protection bits are on in BIOS, or if it's in the SMRAM and all that stuff. Chipsec has a way to verify ROMs that you just pass on as a parameter.
So it's actually going to pull, the chipset will actually pull off in some method the existing firmware and do a comparison to the file that you provided.
No, what it'll do is it'll ensure that the write protection bits are on. But if you want to verify the SHA, you either read out the SHA from the TPMs on the chipset or contact the OEM or the manufacturer for verifying.
Thanks for the talk. I think you did a good job considering the mic issues. You really, yeah. Just now this working. Okay. I think there's ghosts in the wires. Can you trust data returned via the SPI from the chip you're reading? Like, is that like returning of data? Is that handled by the firmware itself, or is this like a pure hardware thing? Or could you potentially mess with that if you manage to infect the firmware?
So every time you read out from the firmware, there's a small chance that you have corrupted it, or that you have read out a bad firmware. So yes, those things happen, and the way to verify it, so if I get a question right, if you want to take out firmware and verify that's the right firmware which is on the chipset, is that what you asked?
If you can trust what's returned from the SPI.
Yeah, so assuming that what's on the SPI chip is correct, there are corruptions that happen when you copy out. The way to verify that is either you do it 2-3 times and verify that the SHA is right. Now, assuming that what's on the SPI chip is also not right, then we have bigger troubles. But the image, so let's say you read out 3 times. The SHA of all the 3 times without any writes to the SPI chip should be the same. And that's how you verify.
What I think he's asking is the firmware itself is not involved in reading out the image. What I think he's asking is the firmware itself is not involved in reading out the image from the via SPI. So barring a whole other level of exploit against like the mask ROM of the chip, which is unheard of as far as I know, you can trust what you actually read out via SPI.
So the SPI, yeah, the BIOS has a header, and you just read out according to the header parameters on there, which is what the flash ROM and bus pirate detects. But yes, if your firmware itself is bad, then you better not look at it.
Well, based on his question, I just wanted to know if there's like a database that you can download and just verify while you're offline, or if there's a database, something like VirusTotal, that you can just upload your firmware and just know what's happening. That was my first thing. My second thing was, if for some reason I believe that I've been compromised, let's say I'm a company, how would I go about to just trying to go back and trying to do like forensics, like firmware-wise?
So as far as I know, there is no VirusTotal database for firmwares yet. But if you follow UEFI parser, there are a few dumps out there which match. Coreboot has a few. There's a guy called John Lewis who has a few ROMs out on the internet. But there's no official database of firmwares. The second thing is, how can you do forensics on firmware updates? I would track the CMOS bit, the CMOS registers, because that's where all the BIOS settings are. And if anybody has tinkered with it remotely, it would be in the CMOS registers. But if you have local access, like there's no BIOS password or there's no badging into your lab machines, then I would first make sure that local access is restricted, and then monitor the CMOS register bit for activities.
All right. I think we're out of time for questions.
Okay, I'll be hanging outside, so feel free to come up.